Welcome everyone. In this lecture we are going to discuss digital signal processing, and the topic which we are going to discuss in this lecture is convolution and correlation. Okay, so let's start with basics of digital signal processing. So what is a time series? When we say digital signal, a digital signal is a time series. What is a time series? A time series is an ordered collection of numbers. Okay, so what does that mean? Let us say there are numbers which are occurring in an ordered way. For example, consider this a cricket match, right? Let's say there are two teams, Punjab team and Mumbai Indians team, and as people are scoring, the scores are increasing. Let's say on the first ball, one score, second ball, there were 2 runs, then total became 3. Then on the third ball, no score. Fourth ball, there was a 6, so total became 9. In this way, the score is increasing. So, but if you see the score at the sequence of how score is increasing with every ball, this is an ordered collection of numbers. So that is one kind of time series. But you can do another kind of analysis with the same kind of data. So you can also consider the number of scores in every over. In the first over, as you can see, India scored, let's say 7 score, and in the second over, India scored, let's say 6 scores. So in this way, if you see, this is also a time series, an ordered set. I can ask what happened in the 10th over, how many scores did India score. So this is an ordered collection of numbers. It's a time series. Basically, time information is there present. So the sequential ordering or the temporal ordering is there of the numbers. Okay, another example could be temperature. How temperature changes with month. So in on the January month, the average temperature is this much. February average temperature is this much, like that. Or minimum and maximum temperatures are this much. So this is also a time series. Another example could be, as we are doing in this course, audio. So audio is also an ordered collection of numbers. So if you remember, audio means my diaphragm of the microphone is vibrating, and the position of this, let's say the center point of the diaphragm, this position is a number, and as it is changing with time, that data is recorded, and that's a time series. So the x-axis is the time and the y-axis is the information which we are interested in, which means the center point of the diaphragm, the position of that. Okay, let's okay, now when the signal is changing, when the signal is coming, it is a continuous reading, right? Let's say the position of diaphragm, I can measure it at any time instant, and it's a continuous reading, right? It's continuous in time and continuous in magnitude. So both x-axis and y-axis are continuous. But now we are studying digital signal processing. So if we have to process this signal in our computers, we cannot deal with continuous data. Why? Because our computers are digital computers. So they are not analog computers, they are digital computers, which means they can store numbers with a finite precision and only a finite number of numbers. Means they cannot store continuous values. They can only store discrete values, and which also have finite precision. What is the meaning of finite precision? It means the number of digits after the decimal, they are fixed. I cannot save an irrational number like that. And I have fixed precision. That means fixed number of digits before the decimal as well as after the decimal. So that is why I need to convert this signal, this continuous time, continuous in amplitude signal, into discrete in time and discrete in amplitude. That is sampling and quantization. Sampling means I am discretizing it in time. Okay, let's see, this is what happens. So I am not going to save the value of this signal at all time instance, but I can only save, I'm only going to save it at 0.0, 0.1, 0.2, 0.3, 0.4, like that. I only want to save these values, and other values I am not going to save. But of course, I can interpolate and get those values, but that is an approximation. The exact values I am not going to save. Now, this was sampling. Sampling means I have already gotten the discretization in time. Now, what about in amplitude? Now, let us consider this value. It could be 0.9999999 and so on, and I cannot save that value in my computer. I can only save 0.99, let us say, if I am considering only two numbers after the decimal. So what happens is this this will be, you can say, rounded off, or it will be approximated by that value. So what it can be seen in more principled way is that you have a grid in the y-axis also, and the values can lie only on this grid. So when I form this grid, you can see many values are off from the grid points, from the from this grid lines. That is why I quantize it, which means I bring these points on the grid. Let's say this was slightly away from the grid, it comes to the grid. This point was slightly away from the grid, it also comes in on the grid. So this is called quantization. I have quantized my values to certain fixed levels. So this is sampling and quantization. Okay, so we are discussing here now, how do we analyze time series? A time series can be analyzed for different purposes. For example, I have a time series. I want to compress the data. As I had shown in the last slide, that if it's a slow changing signal, I don't need to store then all the values at all the time instants. I can save just a few values, and since I know it's a slow changing signal, and I can reconstruct that signal later, right? Imagine let's say an image signal. An image, it has got just white, entire white background, and on the top there is only one alphabet written. Let's say A is written. Now I can save all the pixels and send the information, but that will be very inefficient, because everything is just plain background and only one alphabet is written, which could be A or B or C. Then I can very easily compress it. I can say, okay, my background is always going to be pure white and only one alphabet is there, so very few bits will be required to save this information. That is what JPEG, etc. they use for data compression, basically to compress the data so that it retains all the useful information even when the size is reduced so much. Then next could be data explanation. I could analyze the time series for explaining the data, that why this happened, why that happened. So it's kind of analyzing the data, and what are the factors that affect the data and what are their relationships. For example, you are studying rainfall behavior. Suddenly you observe the rainfall has reduced. Immediately you will be interested in knowing what factor caused it to happen. You will say, okay, let us analyze the time series of rainfall trends, pollution trends, and everything, and then the explanation may be given later by analyzing the data. See, this is because of global warming that rainfall is affected, right? So data analytics can be done, and different kinds of relationships and factors and causal relationships can be found by analyzing the data. Next, data denoising. The time series may have some noise. A very obvious example is when you are speaking in your phone, if there is a lot of noise coming, then you want to denoise your speech and so that the other person can hear very clearly, or you can hear very clearly. So data denoising is a very good example of time series analysis or time series processing. Next, prediction of future values. I have got some time series, I want to predict the future values. Very popular use case is weather forecast. Right? You want to forecast tomorrow's weather, day after tomorrow's weather, like that. I want to check whether tomorrow it will rain or not. So how can I do it? I can look at the previous trends and today's temperature, relative humidity, pressure, and so many other factors, whatever may be affecting tomorrow's rainfall, and I can do a forecast on whether it will rain tomorrow or not. Right. Another application of time series analysis could be classification of time series. As you all are very familiar with this, I think you all use some speech recognition service like Alexa, Siri, Google. So what they do is as you speak, they transcribe what you are speaking. That is a kind of classification. They transcribe when you speak a vowel or a word, or let's say a vowel, they will quickly classify, oh, this is an ah, this is an e, this is an oo, right? So this is time series classification. Similarly, there are so many kinds of classification which can be done. Who is speaking, right? Whether it is a male speaking or female speaking, whether it is music playing, or is it speech, or is it some environmental sounds. This kind of classification could be done. Okay, now let's come to a very important concept for digital signal processing, that is called convolution. So Y is a convolution of two signals, X and H. So when X convolves with H, the outcome is Y. And mathematically, okay, Xn is a real signal. Xn is a real signal where n is the let's say time index, which is a discrete time index, 0, 1, 2, 3, 4, like that. And similarly Hn, here n is the discrete time index, 0, 1, 2, 3, so on. And h of n is a function from the time index to the value of the information, basically. So you are convolving two signals, Xn and Hn, and mathematically it is summation of Xm, Hn minus m, and sum over all the m. So this gives me n, right? M is a dummy variable and n is the actual variable which is corresponding to the output index, output time index. So let us have a very intuitive understanding of convolution. I think just this mathematical definition may not suffice. Okay, so let's come to an intuitive understanding of convolution. Look at this. So understand convolution as a response of a function. Let us say there are somebody, this is a block, this is a system, and it has some input and it has some output. What is the input? Input is hitting. Somebody hits on the drum, on the head of the drum, and the output is a sound. So a sound waveform, as you know, audio is a waveform, sound waveform, where the x-axis is the time and y-axis is the, as you see, the center point of the diaphragm, which is vibrating, so the sound signal. So this is a function, or it's a block, or it's a system which has some input and some output. So the input is x and the output is y, and the intrinsic response of the system is h. Okay, we'll see that. So okay, let us first have the intuitive understanding. Whenever it happens that I have a system which has some input and some output, then how do I model it? Let us consider this. Now I hit harder. So see, the amplitude is double, let us say. So earlier I had hit with let's say some amplitude, some force I had applied on the head with my finger, and now if I apply double the force, what will happen? What do you expect? Yes, the sound will be same, but it will be amplified. You will hear, let's say, double the amplitude, double the strength or intensity of the sound, right? So okay, I'm assuming this system is a linear time invariant. If you don't understand those terms, ignore it, no problem. Just that this is a linear system. that if I apply double the force in the input, I get double the response in the output. Okay, now what happens if I hit later? If I hit after some time, not at t equal to 0, but let's say at t equal to 2 seconds. So what will happen? The entire sound will be shifted, right? Very intuitive. The whole thing will be shifted by 2 seconds and I will get the same response little later. Okay, I hope this part is very clear, that so the convolution can be understood as a system which has some input and some output, and depending on how I modify my input, my output is also modified in the same way or similar way. Okay, let's see now what happens if I have multiple hits. Now if I hit the head twice, once at 0 seconds, then another at 2 seconds. So if I hit it twice, what will happen? So I will get multiple sounds, right? I will hear it twice. So since this is a linear system, I can simply add the two responses. So my first sound and the second sound, that means the sound with a delay, they both get added, and what I hear is the sum of these two. So my Y is basically the sum of these two signals. Now, okay, let's look at the mathematical analysis of what we studied just now intuitively. So mathematically what happens, I can say my hitting is x of n, the input xn, and in this case this is a Kronecker delta function. What is Kronecker delta function? It means at n equal to 0 the value is 1 and everywhere else the value is 0. This is a discrete time signal or a digital signal, so which means my x of n is when n is 0, xn is 1, otherwise it is 0 for all other n. Now this is my xn, my input. What happens at the output? My output is y of n, but my output, okay, in this case, okay, consider it as h of n. So my output is h of n. Why h of n? Because if I convolve h of n with delta function, the output is h of n only. So my y of n is equal to h of n. Now, okay, what happens if I hit harder? If I have a times delta n as the input, what happens to my output? My output will be a times h of n. Okay, a times h of n. Now what happens if I hit the head little later? The input will be delta of n minus capital D. Why n minus capital D? Because now my delta will be equal to 1, my input will be equal to 1 whenever the n minus d is equal to 0, which means my n should be equal to capital D. In this case, if the d is 2 seconds, or sorry, it is not seconds anymore, it is discrete indices. So when d is 2, then this means that my delta will be equal to 1 when n is also equal to 2. So that is why I have represented it as delta of n minus capital D. Now what happens in my output? My output will become h of n minus capital D. What else, right? So this is the same response later. Now let's look at this multiple hits. Now my input is delta n plus delta n minus capital D, right? This is my input. What is my output? It's h of n plus h of n minus capital D, right? So the output is the sum of these two. Now I can do an overall analysis of convolution. So my definition of convolution was y of n is equal to xm hn minus m summation over all m. How do we analyze it? This example, my x of m is basically delta n plus delta n minus d, which means it is 1 whenever m is 0 or m is d, right? And everywhere else it is 0, x of m is 0. Now if I put this this thing in my equation of yn, what I get? My yn is h of n plus h of n minus capital D, right? It's very intuitive. So you can just put the values in there and you will find it. So, and that is what actually we were expecting in the output, right? We were expecting my output to be h of n plus h of n minus capital D. So which means my formula of convolution works. It works. This is the intuitive understanding how convolution works. Basically, if my input is shifted in time, or it is linearly or it is let's say multiplied by some constant factor, then my output is also accordingly changed. And h of n is called the impulse response. It means the output of the system when the input is delta n. You can put the values here. If my xm is simply delta n, my yn will be equal to h of n. Okay, now let's look at a graphical understanding of convolution. Let's look at this formula first. Yn is xn convolved with h of n, which means xm hn minus m summed over all m. Now xn is a discrete time signal, a digital signal, where it takes values 1 at 0, 4, 8, 12, and everywhere else it is 0. And h of n is a very small signal. It takes non-zero values for 0, 1, 2, 3 time instants, and it is 0 everywhere else. Now I want to compute y of n, which is basically xn convolved with h of n. How will I do it? Okay, I can put in the formula, but what is the graphical understanding of doing that? Let's look at this animation. Okay, now let's look at y of 0. Y of 0 means n is equal to 0. Okay, let's go back to our formula. If n is 0, my yn becomes, or y0 becomes xm h of minus m summed over all m. So what I have done here in the graphs, xn and h of minus n. So I have plotted xn and I have plotted h of minus n. Right, h of minus n is simply flipped version, and you now do element wise product and sum over everything. So if I do element wise product, x0 multiplies with h0, you get some value, let's say 2.7 or whatever, and you add, basically everything else is 0, so only this value remains. So y of n becomes what it becomes. Now go to next, y of 1. So what happens at y of 1? At y of 1, my formula will become x of m h of 1 minus m, right? So which means my h of minus n will be shifted slightly. It is shifted so that you can see my x of 0 multiplies with h of minus 1 and x of 1 multiplies with h of 0. And if I take an element wise product and sum over all the entries, I get y of n, which is marked with the orange circle. Similarly, to compute y of 2, my h will be shifted further by one step, and I again do element wise product and sum, and I get y of 2. Similarly, in this way I can keep going. So okay, so what we discussed was convolution with zero padding. With zero padding means I am assuming that my my h of n gets multiplied with x of minus 1 also. But let us say x of minus 1 is non-existent. Then how do I do? Which means x of minus 1 is non-existent, so my h of n cannot multiply with it. Let me show the graphical thing. Okay, so then my this thing will start from here. Now see, this formula is not applicable. The formula which I have written, general formula, is not applicable. It will be slightly modified to incorporate this. So try to understand this convolution without zero padding only graphically, only visually. Don't go by the formula. Formula will not work here. Formula means some shifts have to be introduced. Basically, you do not have x of minus 1, x of minus 2, and similarly you do not have x of 16, x of 17. So you have to only confine yourself to whatever is available. Those values are unknown, right? So I multiply x of n, h of minus n, and do element wise product, and that's what I get. Now move it to the next thing, and again you get y of 1. Then move it to the next thing, you get y of 2. Okay, now let's look at another concept which is very much related. It's called cross correlation. So the purpose of cross correlation is to find similar segment shifted in time. Okay, which means if x and h are similar, then their correlation will be very large, and if they are dissimilar, correlation will be small, close to 0. Okay, let's look at cross correlation graphically. Now y of n is xn cross correlation with h of n. The formula is on the right, top right, and xm hm minus n summation over all m. You see there is no flipping, so xm multiplies with h of m with some delay, so there is no flipping of h. Like in the convolution thing, we had h was flipped by negative, so the h was flipped on the x-axis. So but here it is not flipped. So let's look at it graphically. I want to compute the first entry, which is actually y of minus 3. So if I have y of minus 3, which means n is minus 3, this means my x of m multiplied with h of m minus minus 3 means h of m plus 3. So my h is shifted towards the left by 3 steps. And this is what I get. Now I do element wise multiplication and I get the outcome. Now, okay, although the I am computing for n equal to minus 3, but my y of n, if I compute this in the computer, it's a vector. So the vector indices are from 0. That's why what I'm plotting on the on the screen, y of n, the n here refers to the indices of the vector, and but the time indices, if you consider, time index is minus 3. Okay, now let's next y of minus 2. Now h of n gets shifted by minus 2 by which means h of m plus 2. Similarly, so same element wise product and summation over everything. So then similarly y of minus 1, and in this way I can keep going. Now cross correlation without zero padding, which means x of minus 1, x of minus 2 are unknown. I don't know them, so that's why I will be only considering my y of 0 is actually x0 h0 xm hm summed over all m. So this is what is, I multiply x0 with h0 and that's it. That is my y. Now to compute y of 1, I shift my h towards right, and again I do element wise product. So now I see h of 3 gets multiplied with x of 4 and I get non-zero value, and that appears as y. Similarly to compute y of 2, and this way I can keep going. So this was all about convolution and correlation. Convolution is basically transformation of a signal by a system. The system has some input signal which gets transformed by the h of n, and we get y of n, which is the output of the system. And so this is the transformation, and the h of n is a characteristic of the system. It's called the impulse response, and y of n is equal to h of n when x of n is delta n. So whenever the input is an impulse function or a Kronecker delta function, the output is h of n. Then we looked at correlation, which is used for similarity check. How similar are two signals or segment, let's say how similar is the h of n with some segment of x of n. Okay, and the references for this lecture are here. Thank you very much.